I'm glad to be here. I'm going to present basically the work we are doing at Omnius. And it's basically, I'm going to give you a quick overview of the company itself, and then basically walk you through one of the products we have, or basically a part of the product pipeline. So, and finally give you some outlook of what we were also working on, and trying to make the talk a little bit technical, because I learned that this is a technical conference, so, and also I'm a techie, so I'm trying to give you a high-level overview of how, let's say, one of our pipelines actually works. To motivation, actually it's quite simple. If you look at, actually we're coming from a document processing background, and last year, basically when we were looking at what could be a nice business case to work on, we actually came to the conclusion the insurance industry is a very obvious kind of customer because of two reasons. They have a large bunch of documents, and their process currently is completely manual, which basically means they're processing millions of documents with hundreds of pages or tens of pages every year. And that involves different documents. I'm going to talk about this. But the problem is basically for them is that in order to, I don't know, make their service better in the sense that make it faster, but at the same time also, extracting more information about the customers, doing data-driven like solutions or data-driven decisions on how to evaluate risk and how to make better policies and stuff, they actually have to become data-driven instead of process-driven. So the idea is basically removing the manual burden, or trying to make the manual burden a little bit less time-consuming, and really giving them the ability to really have all the data in their data bank or in a data lake, basically. So that's like a pitch deck, pitch presentation of what we really do in a nutshell in one slide. The basic idea is you're actually receiving documents in different types. They can be structured like a form, they can be unstructured or semi-structured like claims or invoices. And they can be also completely unstructured or very unstructured like policy documents. I mean, usually that's a bunch of pages, and there's a few interesting informations in there, so it's a little bit difficult to extract. The general idea is that you actually want to extract the most important information from it. So of course, that usually is customer information, which is kind of simple to extract because it's mainly names and addresses and stuff. But then of course you have stuff like dates, termination contracts, date of change, and things like that. You want to know the annual price. And of course, if you, for example, do policy comparison, which basically means you have a policy as a customer, you just want to have a better one, either lower price or better coverage, you need to know what's actually covered. So it's actually about extracting certain important things like what are the ratings, what are basically different coverages and stuff. And also you want to know, maybe sometimes you want to know, is your bike insured? Pretty important in Berlin, because bikes usually get stolen, so having a household insurance which doesn't have bike coverage is kind of useless, because bike is maybe the most probable case where you need an insurance for. So I think that's basically the idea. And of course, with this information, I mean, you can actually do multiple things for the customer. So you could either make him better offers. You could actually make sure that his claims, like when he has a damage, get processed faster, because you basically remove the manual check of these things. And our, let's say, value chain of the company is kind of, I mean, it's basically in the whole like value chain, even up to like fraud detection and things. But of course, the problem starts that you actually have to extract the data in some way first. And you may not think about this, but maybe it's, but I think if you look at most of the documents received from insurance companies, they're still on paper. So actually, everything starts from paper still, which is kind of surprising nowadays, but that's the reason. So actually, we are starting, like, the main focus we currently have on is to really reliably extract the data from paper. And it can be digital document, like printed documents, it can be handwritten, and so on. And I'm going to give you a few examples later on. So a little bit quick wrap up about the company. We started in 2015 already, but initially we worked mainly on handwritten documents and from historical books. That was like the initial use case. And since last year, we actually shifted our focus towards a more, let's say, valuable business case, which is the insurance industry. We're currently sitting in Berlin, having US subsidiary. We have some enterprise customers in 6 different countries and 2 continents currently. I mean, we try to focus on a few countries first, because as you know, languages are different. So having, information extraction, of course, is kind of language dependent. So it's better to focus on a few. We have quite a large scientific background in different domains. So there's basically computer vision, machine learning, also artificial intelligence and NLP. So, and actually we have quite a large track record, at least in the past, of from the team, like for publications. Some of the USPs, I think, what we have in our domain is really that we try to actually make the thing completely scalable and with global coverage. So it actually relies, if possible, as much as possible on cloud solutions. Of course, that's not always something the customer wants. So we are actually able also to deploy stuff on premise. It's basically process-less integration, so everything is using common APIs, REST APIs to basically submit documents and things. So the integration is kind of easy. We are maintenance-free and have like teachable IA, so we try actually to as less as possible to rely on things which are like regex or rules or other things. And we have pre-trained models for a variety of use cases because we actually have a large data set of various documents. So we have actually the good opportunity, especially when you think about deep learning, to really train like large-scale models for certain tasks. So if you look at the insurance industry itself and look at the documents you have, you usually end up with two different use cases, as I already said. It's usually either policies, which basically means the contract you have with your insurance company, or the other documents you have, and there are much more, of course, are the claims. So basically you have a damage in your car, or you have a damage, someone steals something from your house. You basically have to file a claim, and then you get the money back. And if you look at the different documents here, and this is really, I mean, one of the issues I had with this presentation was basically I wanted to show you real customer documents. Of course, I cannot do that because there's a lot of sensitive data on it, and according to GDPR, that's even, it's even more difficult to actually show these things. So basically, I tried to collect a few things which kind of resemble typical documents we get, and also later, some of the examples I actually will show you are kind of, they're not synthetic, but they're basically, I did some examples specifically for this presentation. In order to show you a few examples. So, I mean, if you look at it, it's basically a mixture of structured documents or, like, say, semi-structured documents. You have stuff like handwritten printed forms, which are handwritten. You have these kind of tabular things, which are invoices, and so on. So it's quite a wide variety of documents. Sometimes you have even photos and stuff, and this information, sometimes they're actually valuable, the photos, to extract information from. Just think about a car crash. You may want to extract the license plate from the document itself. So we're actually dealing with quite a bunch of documents itself. The talk today, I actually wanted to focus on the forms because that's kind of interesting, and I think it's, since there were already a lot of NLP topics, I thought it's maybe nice to go a bit back and have a look at computer vision a bit. So how does this typically look like? So an interesting thing in Europe is that usually you have this kind of form for the accidents. So I'm not sure if everyone has this in his car, but that's actually quite common. It may look a little bit different from country to country and from insurance company to insurance company, but basically this is how it looks like. You may have some additional things in a typical car claim. So when you send something to your car, to your company, insurance company, you may have pictures of the broken car, you may have some bills and stuff, and I basically made it just blurry, so it's still like not really sensitive. Real-world challenges with this. So let's looking at the forms. You have different ways of the same form basically representing information in different layouts. And you have also, of course, depending on how people scan it or how they actually, nowadays people don't scan anymore, they actually photograph stuff. You may end up with, let's say, horrible versions of this form. I would say currently we can handle up to here. I think we don't really have a solution for this yet. That's something we have to work on still. And this case is it's there quite often. So it's definitely something we'll have a look at. I'm still not sure if the effort is worth, let's say, the 10% or 5% of documents which look like this. And you may just go back to the customer and say, please send me a proper one. But that's how it is. So how do we deal with this? That's basically the complete pipeline. I'm going to go over it in a little bit high-level way for you, because, of course, there's some nitty-gritty details which I cannot really tell. But basically, it's this kind of process steps. So it starts with page classification, which basically is if you get a document with multiple pages, you want to first detect the form page, essentially. And we use some deep learning-based methods for that. Then the template alignment is actually making sure that we actually try to basically detect the fields. And we're detecting the fields in such a way that we actually know where the fields are. So it's more or less, and the goal is actually to align the model we have to the page. So it's mainly an alignment task, not really a detection task in a sense. Sometimes we have to detect text lines, which means like if you have multi-line fields, and in this document it's not that much, but in other cases where we have, you actually have to detect the text lines. And ultimately you want to recognize the text, so basically the red things here, and I will show you a bigger image later, is basically the recognized text. So let's go a bit in detail about the steps. So as I said, page classification is mainly about splitting documents, and the idea is that you can use this for multiple purposes, but of course the main challenge is to detect pages of interest and get rid of all the garbage you don't need, and also to maybe, sometimes people want to know if there's photos attached and things like that. The current approach we use is basically a convolutional neural network. Actually, you can see kind of the architecture on the right. It's a well-known architecture called SqueezeNet. We tried different things. At the end of the day, SqueezeNet was so far the best model we had, simply because also the data is quite limited we have. So training an inception network is a little bit difficult with the due to the lack of data. What we usually do is we train it on, we basically try to do transfer learning on multiple tasks, because sometimes we just get 100 documents or 10 documents per class, which is basically impossible to train. And the current results are essentially like 96% for something like between 10 and 15 classes. And the cool thing is it's actually very easily adaptable to other tasks. Like a typical task is also when people scan documents, they put a barcode on the first page of a document. So they basically can scan in batches. And then you basically have to detect the first page, the barcode, to know where the first page actually starts. So that's also a kind of interesting application of this. I think the network is not that interesting. I mean, it's basically a FHIR module, which is essentially kind of reducing the dimensionality and then putting it back up, and then there's a few layers of this. So it's kind of an existing architecture. The interesting thing is, how do you train documents from scratch? There's no ImageNet for documents, so there's no document net. So basically, what we do, we actually start with ImageNet, pre-trained models, and interestingly, the lower levels of the network are actually kind of generic, even for documents. Of course, you have to actually retrain the upper layers, because documents are black and white, and you don't look like, you look actually for more like structural things, like binary features, than like typical natural image features. So basically, we retrain the network with some open source, like open databases, and we also basically then we usually adapt it to the task at hand. So usually we retrain the model for new projects. Just some numbers. This is one example. I think we have used this whole pipeline now for 6, 7 different projects, and usually it works quite well out of the box. This is basically confusion metrics, different classes. So here, for example, we had 2 different forms with 2 pages each. So that's actually not the European accident form, that's a different one. We had envelopes, we had train tickets. So that was mainly for, I think, for a train claim thing, a use case. And you can see the confusion metrics basically shows that we're really good actually on the form pages. There's no confusion, so basically confusion metrics is basically optimal if everything is in the diagonal, and all the other numbers should basically be 0. So nothing is confused, basically. If you look here, there's a bit of confusion in the lower bottom corner, which is due to the fact that the train ticket is sometimes, some train tickets are actually considered other by the customer, because it's maybe not a train ticket, but a public transport ticket. But of course, visually, they're quite similar. So this is one of the examples where it doesn't really work that well, but on the other hand, we're not that interested in this part anyway. That's the most important part, is that this actually gets properly detected. So, to the template alignment, the point is here basically, as I said, is not about detecting the individual fields. The basic idea is this is the input, this is the template we have. We know that the document looks like this. This is what we get as input. And we actually want to estimate kind of a motion model between this and this. So it's a typical computer vision task. And of course, you can define different models. So you can basically, if you know it's a scanned page, you actually don't need to consider like perspective transformations. You just consider affine transformations, which limits the transformation you have to estimate and makes the thing more easy to detect. We use 2 different approaches. We use a feature-based approach for photos, because it's easier to actually do the mapping between the 2 things. And for like scans, or actually doing the fine-grained alignment at the end, we use a dense pixel-based approach, actually. So again, this is just a big picture of how this feature-based thing works. Idea is you find correspondences between the pictures, and if you have enough of them, you can actually estimate a transformation using an iterative optimization approach. Just an example on how this looks for, let's say, scan pages. So you see there's slightly rotation, there's a little bit of translation. What we actually do is, this is kind of the representation we use internally. You see actually it actually gets rid of most of the text. So the problem is, of course, if the text is not in the template, so you shouldn't consider the text for matching. And actually, the representation basically removes this part in most of the cases. And just to give you an example on how the alignment looks like, this would be without the alignment. So you see the boxes actually don't match the text. If we do alignment, basically this is how it looks like. So the idea is that actually usually we are not changing the document, we're basically moving the boxes around, not the document itself, because that makes stuff just faster and we don't have to store more images. Some text line detection. So the idea with the text line detection, I think I'm quickly going over this because this is not so relevant for this use case, but for other documents is basically, in some cases you have multi-line fields and you actually want to detect these lines. So in this case, we actually adopted another object detection approach, which is usually made for objects. It's this YOLO-based approach, which tries to do two things in parallel, which is essentially classifying basically grid squares if they contain the object or not, and basically at the same time trying to estimate the bounding box of the object itself. And it's called YOLO because it means you look only once, so you do these two tasks actually in parallel instead of sequentially. Was the typical approach so far? Some examples for a kind of different documents. So you basically see it detects the text lines and even is able to actually, if they're slightly rotated or tilted, actually detects also the angle of the text lines. It doesn't work that well until now for really upright things. I mean, it kind of detects it, it's still a little bit off the angle. Okay, final step. So we know where the boxes are, we just don't know what's written there. So how do we go to fall for this? Again, it's a neural network-based approach. And the idea is essentially, the input is this, and this is the output. So basically, we train the system based on the text lines we have detected. And the problem is basically the network doesn't know, and this is the main difference to a normal NLP task, is you don't know where the letters actually start and end. So you cannot simply take a letter and classify it. It wouldn't work. So basically, you slice and dice basically the image. You have a CNN to actually model this part. And then you have an RNN to basically distribute or get more context for each of the slices. And at the end of the day, you have the connectionalist temporal classification thing to actually give you back the letter. So the question is, if you would just take the slices, you would have TTOOO as a sequence. And of course, TTOOO is not the right letter. So the CTC basically takes care of, it's basically like a decoding, it's like a lattice, basically, kind of a tree with different transition probabilities between different letters. And basically, the CTC takes care of decoding this into this kind of sequence into the real letters you want to have. So some example results. I hope it's visible. I tried to actually make it in such a way that you can see the overlay. The red one is basically the recognized result, and you still see underneath the text, which is a little bit messy. But I will show you some really later. I may show you some other things. So the idea is basically here you see, for example, the name of the guy is Verrier, and it's called recognized as Verrier. There's Jordan. So most of the things are actually correct. I mean, that's a pretty good example because the handwriting is kind of easy. You have some, I think that's also correct. I think that's more one of the examples where basically you get most of the letters correct. The important thing here is the whole text recognition approach doesn't have any knowledge about, there's no language model behind. I mean, at least not an explicit one. So we don't know what names are there, we have no assumption on what cities are there, so all these things are actually done afterwards. The reason for this is we want to apply this model like ad hoc in a new scenario, so we don't want to really train it on a dictionary of things. For like cities, for example, you could basically train it on a dictionary, and then it's basically a word spotting task. But of course, this limits you to use cases where you already have all those databases in the first place. So some things about validation. So of course, as I said, the problem is we don't do any validation. So issues you face is that sometimes one single character is wrong. What can you do with this? An easy solution for, let's say, stuff like peoples and places and things is, of course, to do kind of a fuzzy matching thing. Essentially, this could be the input thing, and the output should always be Hewlett-Packard. And that's basically kind of a fuzzy matching an arrow, like you use Levenshtein distance to basically match certain words to a database of words. That's kind of easy to do. A little bit more complicated is the case when you have kind of free text descriptions. Like imagine you have a health insurance thing, and people basically write down what kind of disease, like sickness they had in the past, like you had a heart disease or something. this is usually free text, so it's not really like a keyword or something. People write down, they may write a long sentence or they may write short description of it. So you have to map these things usually to a database. So you have, the insurance company just basically wants to make a tick in one of the checkboxes, like what kind of heart disease did you have? And then basically it's matching a description you have from the text to a description in the database or something. So for this we use something called Siamese networks. So the idea is essentially you try to train a distance, it's basically a matching task. So you try to have a distance function which gives you 0 or low distance for related things and a high distance for other things. And how this actually works is basically you train actually one neural network, but basically you train it in 2 different ways. You basically put 2 input data there, like one relevant item and one relevant item, and you make sure that the distance actually becomes small. And at the same time, when you put a relevant and an irrelevant item, you want the distance to become large. And since you train these networks are actually essentially the same network, so you make sure that the weights are actually adapted in the same way, you actually can make sure that the distance function you get at the end, like the neural network basically implements a transformation to get from the features to a new feature space. You can actually make sure that this kind of thing can be learned, and it's not like an Euclidean distance or something like that. So this was basically just the thing in large, if the projector would have been small. So give you a bit of outcome. Actually, I prepared a demo. Unfortunately, my laptop doesn't work. Maybe we can try it later again. Or I just show you later if someone is interested. Basically, the idea how it currently works is basically we have like this web service, you upload your documents, and after processing time, basically you get a validation interface. And the whole idea of this process is that, of course, at the current stage, machines are not perfect. That's the first problem. And if people think AI solves everything automatically, it's kind of the wrong assumption, I would say. Second thing is that still the customer needs to make sure that the data is actually correct. I mean, nothing is worse than if we extract, let's say, the IBAN number in the wrong way. I mean, we put the wrong number and the people transfer the money to the wrong account. So the way we do this, actually, we have this kind of validation interface, and this is especially for the EAS form. So the idea is that we have the kind of a visual representation of the extracted information, which is similar to the previous thing. You can basically click on the different fields, and you already see red and green colors. So we also, for each field, we actually know the confidences we have in the extraction. So the idea is that the user only looks at the results where basically something is wrong. And you can see also the confidence is not yet perfect, so sometimes you actually make a small error, but actually it still says it's quite confident. But it's kind of user adjustable as well. And we can actually retrain the confidence value based on the feedback the user gives. So, and usually the workflow would be, he would go through the fields, he gets basically, like when he clicks on this field, he basically gets up here an extract of this part of the page. And basically, you can actually correct stuff. So this is basically kind of, he corrects the one letter which is wrong, basically to a D, and he basically deletes the space in Krause, and then basically he can confirm the thing. And yeah, basically this is the whole idea, to give people a validation interface which makes the whole process faster than if they would do the whole thing manually. But in the worst case, if everything fails, they could still use this and enter data manually. So one of the cases where we have the crumbled example, everything may basically fail, and then eventually the user would still have to do it manually. Some numbers. So how does this actually help business? So this is for one use case. That's why basically the numbers, I think, can be different. So this is basically in seconds. And basically I'm comparing the pure manual process by the insurance agency now and basically the current semi-automatic process. And that's for one specific example where basically it takes them 120 seconds to extract a form. I think actually it's not the EAS form, it's a different one which has fewer fields. I think it has like 20 fields, 25. And by doing the semi-automatic process, actually it takes our system currently 30 seconds, but it's basically scalable, and it doesn't really matter because it's not a synchronous process anyway. You can actually pre-compute this. And then it takes them 40 seconds to correct stuff in average. Of course, there's documents where basically, they don't have to correct anything. That is basically 0. And in some cases, it's actually a little bit more. So, but in general, I think in average, we can actually save 66% of the time already. And of course, there's still a lot of room for improvement, especially because we don't yet really use for example, the fuzzy matching thing we didn't implement for this kind of thing. So the thing you saw with the character error on the name, like Frida, for example, or Krause, these things are easy to correct. And these numbers are actually based without these corrections. Quick summary of the things. So the idea is that, I mean, Omni tries to actually transform the insurance industry from a process-driven to a data-driven workflows. And the idea is that this can be achieved by doing information extraction for all kinds of documents. And the interesting thing is you get more and more diverse documents, the more and more use cases you actually have a look at. Still, handwritten forms are actually very important. And actually, most of the use cases we did so far, there was some kind of handwritten forms, which is actually a little bit surprising, but it still seems to be a valid form, information gathering thing. And we actually can accurately extract data from this using kind of computer vision and deep learning together. And the semi-automatic validation is good for quality and speed. One challenge we currently face is basically different layouts of a form. So we're working on dynamic templates, which are not static. So that's one interesting research part, actually. Robust handling of photographed pictures is, of course, a problem, because people more and more take pictures with their phones. And another thing is actually lack of data. So we're working actually on generative models to do data augmentation, to train better models at the end. So I think that's it for today. Thanks for listening.
Thank you very much, Lutz. Right on time. That's fantastic. It's quite an interesting challenge, definitely, that you're solving. So it's very impressive to see that. So thank you very much.